Alright, so we come back here and we're going to continue with friction. Of course, here you will have to differentiate between the two different friction that I have explained in the previous part 2 of your Newtonian mechanics. So number one is the static, that is opposing the motion, and the other one is the kinetic friction, that is with the motion. So kinetic friction happens when there is motion between the contacting surface. As you know, the frictional force happens when you have two surfaces or two contacting surfaces, meaning like when two surfaces come into contact, you've got a friction. And sometimes kinetic friction is going to support the motion between the contacting surface, and so static friction is going to oppose it. So the static friction happens when there is no perceptible motion, meaning like we do not have the motion. This one is you have a motion between the two surfaces, no motion between the two surfaces, static. Motion between the two contacting surfaces, you have a kinetic friction. So the magnitude, we always need to know, every time we think about the force, we need to know the amount of the force. So the amount of that kinetic friction, yes, depends on the normal force, and the nature of the two surfaces. So you have a surface 1 and surface 2, and we gotta know what they are. So meaning the material of these surfaces, so the nature of the two surfaces, and then of course the magnitude, of the normal force acting on that, surfaces. So we usually write it with a constant, so for friction force, a little f like that, we have normally, write like this, yes. So if you go back to this, I just want to show you, the friction force, that how we wrote it, the Fs, yes. And then of course we come back to here and remember the distance that I talked about, and I'm going to review that for you, yes. So that's how we write it here, so don't forget that. So anyway, so now we are going to write it in a little bit better way, in this way, so you have your F, friction force, and then I am going to put a little K, which is actually this, the same thing, and the constant is now called by mu, K, and then your, of course, your X, this is going to be just an N, which is represented by the normal force, and so your mu K is now, we're going to give a really good name, and that's we call the coefficient of the kinetic friction. It's just a constant. You need this extra number to balance the whole situation of the friction. Without that, you wouldn't have accurate description of that force. So the kinetic, of course, this mu comes from the environmental factors of where we are living, which is our planet. So the kinetic friction force acts in a direction opposite to the relative velocity. So here, the kinetic friction forces, the kinetic friction force acts in a direction, opposite to the relative velocity. Relative velocity, like now when we start to talk about the motion, situation in this way, you've got to trace where you are. And never ever forget your velocity is just an aspect of a motion. The motion always caused by a force, and that's where you are. You're looking at the situation. So the kinetic friction force is going to act in a direction opposite to the relative velocity, which is telling you that the kinetic friction is going to act, opposite to the motion direction. Because every time you see the velocity, you know that something is moving with a velocity. Something is moving with a velocity because there is a force behind it, and that force is opposite to your kinetic friction. That's all it is talking about. So then we gotta get into what is the difference between the static and then the maximum static friction forces. Maximum static meaning like it is going to oppose the motion. Then of course we go into the maximum static friction force, and we're going to write it this way. It's just telling you the friction, and we see this little f, so we know that this is a friction force. And then we know this max is just telling us the friction force is static, as for static, and it is at maximum, meaning that that amount of force got to be overcome if you want to start a motion. Meaning like your two surfaces, you have a maximum friction that is opposing, the motion to happen. So if you want a motion, if you want that surface to slide on another surface, you have to overcome that, okay, friction. And that friction is the maximum friction. So the normal forces right here, and then your friction force is actually equal to the normal force with some coefficient in there to adjust that equilibrium. Of course, the equilibrium got to be broken if you want the surface to go in one direction or the other. Meaning like to initiate a motion. So we will play with this equilibrium. Of course, every time we write the equation, we are going to expand the meaning of it. So your mu s is your coefficient of static friction, s for the static, and mu is the coefficient of the static friction. And of course, it depends on the nature or the material that made up that two surfaces in contact. And then again, we go into the static friction. Again, force is the friction, and it is static. S is for static. It is opposing the surface from going into motion. So here you're going to see that the force of S greater less than or equal to your maximum friction that is opposing, like that. So the friction force, I usually don't say the force, and I just say friction because I automatically know that the friction is a force. So you will hear many people who say friction as friction without saying like frictional force or friction force. So anyway, so friction is gonna exist when no motion is present, because you can also get rid of this because everything that we know are in our perception anyway. So your friction, so you have a friction if you don't have motion. And you can get the friction by applying the equilibrium equation to that system. So meaning like that, okay, there's a friction if the surfaces are not in motion and they are in equilibrium. It's got to be in equilibrium. Like, see, the forces are equal but in opposite directions for the equilibrium to be successful. Otherwise, if one of them is greater, your equilibrium will be disturbed. Then we come to the Coulomb's friction model, which is extremely very, very important, okay, in mechanics. It's because you have your force, your mass, your resultant force going in this direction, meaning your motion. And then, of course, we break down into many different forces on that mass, right, acting on y-axis and acting on x-axis. And this usually is the same, okay? And you're going to play with this too. If your force is greater than this, motion will go. Now there's a motion here, represented by this black arrow going in that direction, so therefore you know automatically understood that friction force is being overcome. So here, frictional force, your maximum static friction, and we're going to put it into graph, and this is where the student get confusion because their brain got to be able to change the graphical representation from x, y coordinates into force and frictional force, okay, coordinate axis. So this coordinate axis is not equal to that coordinate axis because this coordinate axis concentrate only on the forces, and this coordinate axis is now concentrating on the friction force in this, okay? So we're getting rid of that, by the way. So here we're going to put the very first one is the static friction, where the maximum static force got to be overcome. Kinetic friction, the motion, this motion happens. So up to here there's no motion because you're overcoming the maximum static friction, and here the motion happens and keep going, and that motion is this motion, of the object, of course. Then your pushing force is not large enough to initial motion for that to go. What type of friction happens? We know that it's a static friction because it is opposing that, because there's no motion happen. Is the static friction force usually equal to, less than, greater than? Okay, this whole thing, meaning like here is the force, this is the maximum friction, right? Static friction, and of course your normal force, okay, which is acting on it. Don't forget these things, okay? And now you have to understand whether this static friction force is going to equal less than or greater than. Yeah, now it's got to be less than y because you're going in that direction. Okay, not enough. Yeah, initial motion, static friction. The static friction force usually got to be less than, okay, your Fs, a maximum, so you are comparing your static with a maximum. It's got to be less than that. Yeah. Now we will get into kinetic. Kinetic friction is the one that caused the motion. I just want to point out a very important thing here, okay? You got to understand that here, when we talk about not large enough to initiate your motion is your static friction, regular, not the maximum. Here, okay, trying to point out, this is a max, by the way, yeah? And that's the reason why it is less than, yeah? So your static friction force got to be less than your max, okay? If motion won't happen, yeah? Be careful in these 3 slides to be able to understand, okay, this F is not a max Fs, yeah? We're talking about here is a maximum static friction force. It's not the same as this, okay? This is happening right here, like that, okay? All right, I just remember to point that out. Some students don't really get it, and again, you can't just read it to understand. You have to listen to my lecture to be able to understand these things. Okay, you can't just say and blame it on to other people who is English to compensate your deficiency in the effort of studying as well. Okay, so make sure you actually study, put some time to be able to understand these things. All right, so now we're getting into the kinetic, right, friction. So again, we gotta choose larger or smaller. If we want to get, if we want to compare to that maximum static friction, it's gotta be smaller, yeah, because the friction usually decreases as the velocity increases. Because you are opposing, for the motion to happen, you have to be this thing or overcome the maximum static friction. If you don't have the motion, then your maximum static friction, okay, got to be bigger than the kinetic friction, so there's no motion happen. Yeah. All right, and then the next one is you're going to consider a block that's being pushed as shown in this direction. Yeah, so you have an angle, not a straight, all right, on horizontal axis anymore. You have an angle, right, and this force is acting on this mass. Doesn't really matter whether you have an angle or a straight line. We always go with the y and then the x, right, like that. Yeah. So now we draw the x-axis, and then we're going to break down all the forces that is on that object. And we have a weight and we have a normal force, and they cancel. So get rid of it. So now we have two surfaces here, the surface of that block and surface of this gray block. Okay, so they are in contact, so therefore there is frictional force. So now we are going to compare the frictional force with the pushing force. Okay, the pushing force is at an angle theta. So now we will get into it. So if the block moves a constant velocity, it is moving with a constant velocity, and we have to try to find what's going on with it because it is moving. Yeah, the block is in motion. So therefore you got to understand that this been overcome. Yeah, so therefore you have B and E situation happening, meaning like this guy is bigger than that, and then of course your normal force is greater than mg, so which is this two guy right here. Yeah. So what's very important here is it is moving with a constant velocity in motion. Yeah. Now the block is not moving. Yeah, and if the block isn't moving, your static friction is successful. Yeah, so therefore we are going to break down again everything that we need, and then we're going to concentrate this and this. Yeah, since the motion is not happening, okay, and we do have an angle. So every time we have an angle, if we calculate it, we have a force with the cosine. Cosine just comes from the 90-degree, okay, triangle. And if you have like a theta, yeah, you have a sine is the opposite angle, and cosine is the adjacent angle. Yeah, so since your resultant force is there, it is a cosine, yeah, of that of this triangle. Yeah, so make sure that you go back to sine, cosine, yes, trigonometry review. Yeah, if you do not have a trigonometry, please start reading about it. Okay, so then you will understand what I'm talking about. It is not my responsibility that your lack of the mathematics, knowledge, and it isn't fair for the professor to teach everything again from the geometry, trigonometry, all the physics stuff back into here, and you just say, like, I don't understand because the professor isn't explaining well. No, that's not true. That's very unfair. It's just that your lack of this knowledge. If you don't lack the knowledge of the trigonometry, when I say that's a cosine theta, then you should be able to get it. And it isn't fair that the high school, like teachers are not teaching anything, and then just throw all the student into the college and the university with a very minimum amount of knowledge, by the way. And we have to teach everything from mathematics, calculation, algebra, calculus, you name it. And I don't even know what to say. We are very exhausted, okay? And it isn't our responsibility to teach everything that you're lack of. So anyways, make sure that you read the trigonometry, okay? Now we have an AI boom, so please use the AI. I totally support 100%. You've got to somehow get that knowledge, okay? So make sure you review the trigonometry and you're going to understand why this f is equal to this, which is your resultant f with the angle theta, and the magnitude of this amount of the force can be calculated mathematically in this way. So now we get that. And of course, this is our usual sum of the forces on x is going to equal to the mass and acceleration on the x is equal to 0 because we are not moving. Okay, all right. So now what condition must happen to set the block into motion? Now we want to go. So therefore we have to overcome this friction. So now we're going to write that down. And here is the force, magnitude that got to be bigger than this guy there. And the friction is your static friction got to be overcome because static friction is the one that is halting this object, okay, not to go into motion. But we want to go into motion, we want to move. So therefore, you have to overcome that, meaning like this force got to be greater, otherwise motion will not be successful. And this static friction can be calculated, multiply this normal force, okay, with this, okay, mu. Now, if the block is moving, what is the friction force? So now we go to calculate the friction force. You can calculate it by using this, all right, magnitude of this force, which is normal force, times this constant, and constant will always be given to you, because we have already deduced from a long time ago what that mu is, and mu k again depends on the environment, meaning material, this material of that, and the material of, and what's in the environment, okay, of this planet. All right. Now, this is, you just listen to how we do it. Of course, I am not going to ask you about it, but you at least know like how we solve it, and you already have a good idea of how we analyze the force by breaking down into different coordinate axes. So again, we're going to assume the friction force is static, not moving, and we're going to solve the frictional force, static friction. And I only read like this. Force is automatically understood. Every time you say friction, you know that it is a force. We only check like if that's a static or kinetics, from the force balance. So here we have a static. We're going to check if the friction force is static, and we have a maximum, a static friction to overcome. So you can be able to see this static friction is less, so therefore there is no motion in that situation. Now there's a woman, and she is going to exert a constant horizontal force going that way. Of course, every time you think about the horizontal, you're in your mind, you got to have this thing going on. Okay. Alright, so horizontal force on a large box, and as a result, the box moves across a horizontal floor at a constant, speed. Now we have a movement, and we're going with a constant velocity. See that motion is going that way. Got to be in your head. And then this horizontal force, constant horizontal force applied by that woman, we have to choose one of the situation in there. Okay, so number one, it has the same magnitude as the weight of the box and is greater than the weight of the box, and it has the same magnitude as the total friction force which resists the motion of the box, and the other one is greater than the total friction force which resists the motion of the box. So now we are looking at the situation where she is pushing the box. Yeah, it doesn't say uh, anything about this. So when you go back to this, you are going to see, yeah, so it's just telling you the box moves across the horizontal floor with a constant speed. Okay, and this is the reason why this, I'm going to write that down again here. This speed is very essential. If this is going with a constant, force, then she has the same magnitude as the total friction force, which is going to resist the motion bus, meaning like her force, okay, and the total friction force, okay, they are equal. Yeah, that is what we're talking about. So this is a pushing force is equal to the total, meaning like the sum of the friction force. Okay, again, friction can be calculated from the normal force. Now we're going to draw a diagram so you can understand the components of the force. So here's the push force, friction force, normal force, the weight of the box. Okay, this force comes from that woman. The weight of the box comes from the box. The normal comes from the planet and this gray object right there. The friction comes from the two surfaces in contact, yellow and the gray, okay, which is this guy. So understand all of that, and of course your fx is going in the x direction, and we also have other components on the y direction, your normal and the weight. Okay, see this, x-axis and y-axis, yeah. And the sum of that fx, which is this guy, is 0 because it's going with the constant velocity, yeah. And when you use the sum, right, we are looking at the equilibrium of all these forces, yeah. And of course your force, this push force, is equal to the friction force. So if you want this box, right, to go with a velocity or an acceleration, when the velocity changes, you're going to get a different thing here. Yeah, right now we have a constant velocity. It is moving, but it is on a constant velocity, so therefore they are the same. Yeah. So it's a little bit difficult for you to understand because in your mind, every time motion is happening, you always think like the push force is greater, yeah, than the frictional force. Is no, not in a situation where you are going with a constant velocity. Yeah, so that's a learning point that you need to put into consideration. So if the woman in the previous question, she's gonna put a double energy, yeah, doubles the constant horizontal force, and then the box now is gonna move, yeah. Doesn't say anything about the constant velocity, yeah. So you have to come up with this situation and understand now constant speed is now 2 times. That can't happen because we have already break the movement, the first situation, the movement with the constant velocity v0 has been broken, the equilibrium has been broken. Well, the continuously increasing speed is how this object is going, assuming it is a superwoman, because she is putting a double effort and is physically able to run with an infinite speed. Okay, this is just exaggerated. All it says is like, hey, like motion is successful because you're putting double force on it. So a constant speed that is greater than that cannot happen because that constant speed has been broken. So this is automatically out, as soon as she doubles the constant force. For a y with an increase in speed and then with a constant speed. It didn't say either. She just put in a double constant force. So therefore it gotta move, and it's gotta move with a different velocity. Yeah, so that's this one, continuously increasing speed, because she doubled up the force. We do the same thing. We're gonna draw the force diagram here. Double, same friction, same normal, the same weight because mass doesn't change. Acceleration due to gravity doesn't change, okay? And here is our constant velocity. Since we double, we're going to put it in there, put it into here. The motion is happening, so you have an extra ma, don't forget that. Yeah, the first condition doesn't have a double force. We only consider this. Right now you have a double force making a motion, so another ma, which is the one that most of the students forget. They usually write it here. Don't forget this. And this is the extra force that is making. Yeah, extra. This is the force. F is equal to ma is a force. So you have an extra force. Okay, I'm going to just write it down. Extra force. Extra force that is causing that resultant motion. Okay, so your acceleration C has a force divided by mass. Okay, mass doesn't change because it's the same box. Only your force changes. Therefore, you have a acceleration, meaning velocity changes. Now, if the woman suddenly stops, she's going to stop. So when she stops, she applies the horizontal force to the box. Yeah, and then of course we are given 5 conditions right here. So what is going to happen to the box? So the box is going to definitely slow down, of course, because she stops. Yeah, continuously to eventually it is going to stop. This one is wrong is because it's immediately come to a stop. No, because she applies a horizontal force and the box was initially in motion, yeah, and she applies suddenly stop it. So therefore it will slow continuously and then it's going to eventually stop the boxes. Yeah, it won't immediately come to a stop because you still have a force, the pushing force. Yeah, and then the second condition is you're going to continue moving at a constant speed for a while and then slows to stop. This is tempted because it's very much similar to what we are thinking. The only thing is the difference between this. Yeah, so slows is the key word. Here is the continue moving, meaning like you are moving with a speed. It can't happen because you stop it. As soon as you stop it, your speed change. So therefore, this is indicator of why this situation is wrong. And the next one is continue at a constant speed. Cannot, because you stop it. Every time you start, your velocity change. So this is also wrong. And the last one is increase the speed. Cannot increase the speed because you are stopping. It got to decrease the speed. So the keyword slow, yeah, stop, accelerate. Velocity will go down. Okay, so therefore this is the correct situation. Of course, we draw the diagram, your weight, and then your normal, and then your friction, and here is your initial velocity. Okay, we stop, so therefore 0. Okay, and we have a motion that is going, extra force, and then your friction. Okay, and you're gonna get this, and your acceleration. Of course, we use mathematics algebra, and definitely a slowing, which is deceleration. Okay, all right. I'm going a little bit faster to save the time, but I think you get it. Okay, so the above questions, do not compare with me because I have a lot of years of studying this. Okay, so it's in my head really automatically in my head, by the way. So anyway, so the above questions are theoretical. Again, it is what we thought this world is, and it's limited to the human intelligence. I told you so many times, by the way. And human intelligence is completely depend on our structure of this system. Yeah, we have no idea if that's the truth of this universe or no. I don't think so, because there are many different natures that we have no idea what they are. Up to so far, we haven't seen them, so therefore their nature is completely different from us. Yeah, definitely not in our structure. It's got to be completely different thing. They may be here, you just can't see it with your nature, yeah, because they have a different nature. If God nature is the same, then we must have seen it. Some people have claimed that they have seen it, but not everybody have seen it. So the like the spiritual or the God nature is definitely not the same as us. Okay, so anyway, so these are the way that we think, yeah, reason. Again, our reasoning is limited to the structure of our system, which is very fluid. You know, the structure of human system is very fluid, and they exist only temporarily at this region, at this time, at this location of the universe. So anyway, so go back to here, and you have the above equations are theoretical, and I've just explained why scientifically, and then idealized because it's limited to our human intelligence. Now, what will happen in the real world? Now we're going to come back to the human world again. Yeah, inside of the human world, meaning like it is happening on the paper in the book. Now let's think about outside, because you have an environment outside. Yeah, so the outside real world environment is different from the environment that we theoretically set up on the page or in the textbook or idealized. Not simple as this. Yeah, not systematic as this. There are lots of external forces on her and on the box. Yeah, so that's what you need to reason. Okay, in example 5.4-3, of course we don't really go into the situation, because you understand that if you think about the real world, you will consider the external forces, yeah, on it, instead of we simplifying it in the book. Okay, then we will get into the free body diagram, how to represent the different components of the force. So now the first free body, FBD, means that that's a free body diagram. And of course here is a situation with an inclined plane. We have two surfaces, the gray and the orange. The orange is an object with a mass, and the gray is inclined surface with an angle phi on it. Okay, and now of course our force on that object M is going to be at an angle, to this. This is just a reference, a surface where this angle was measured. So the angle is from here to here, that much, theta. Okay, so when we want to draw the free body diagram, you have to come up with the orientation. So when you look at it, our orientation is definitely this, definitely not this. So that's what is showing incorrect body orientation, because when you look at this situation, you know that the mass M, that object is positioned in this way because of this inclined, object right there. Then we're going to come into here, so we know that this is correct, and then we're going to bring in our coordinate axis, your x and then y. Yeah, the x and y got to be always perpendicular to each other. Yes. Then we are going to put in all the forces on that object. So now we have, here is our object. So therefore we're going to come up with our weight component. Since the orientation is at an angle, we have to account for all the angles. You don't have to remember all of it if you just listen to me. So we will go with the mg sine theta because of these angle that the position or orientation of this object is. Okay, so this is very important. Again, every time we use a sine and cosine, we are looking at this triangle. Yeah, so which is this guy. And you're going to get mg sine theta. Please review your trigonometry so you understand how this mg sine theta phi is come, with this angle. We have two distinct angles. Of course, your f is going to go with the f cosine. Okay, cosine is adjacent, and sine is the opposite angle. So I see there's a little a pink arrow. It's showing you cosine means adjacent side. Sine is the opposite side of this angle. Angle adjacent to the theta. This is opposite to the theta. You can be able to see it. And of course, you have f sine f cosine theta and f sine theta in that direction. Okay, so now you can see that all of the coordinate axes are drawn in the free body diagram. We're going to write our normal, and normal again got to go with this x and y axis. So therefore on this y axis, your normal force is mg cosine phi. Your weight mg sine phi. Your force is going to be the resultant of this. So now we are going to draw everything here, and we have a force, we have a normal, we have the weight, and we have this kinetic friction opposing that force. So now we are going to use the component forces. So component forces is going to be the mg cosine phi, mg sine phi, to account for this orientation of this. We just tilted it a little bit from the 90-90. And then of course your f sine theta and then f cosine theta are acting on it from this force. And then of course your friction is going that way. Alright, and then we will get into a girl is getting ready to jump off of a driving board and into a swimming pool, and her legs are flexed and pushing on the board so that her body will accelerate up and forward. Okay, she's gonna go accelerate up and then forward because she is gonna dive into a pool. Now the body is gonna accelerate up and then forward. meaning like that. Okay, you're gonna go with the acceleration. Her mass is like this, her direction is like that. And first she's gonna go up, and then she's gonna go forward. So at the instant right before she loses contact with the driving bolt is right here. Since she moves up, she's gonna come into the air from the board. It means like she loses contact with the surface. Yeah, and then draw a free body diagram. We have to draw about her force. So let's take a look at it, and we start drawing her weight, normal, friction, okay, and here's the board. Yeah, so since her forward force is that way, okay, going up and forward, she will be opposed by the frictional force in this direction. Yeah, so the body will accelerate up and forward at the instant right before she loses contact with the driving board. She's going to draw a free body diagram, which is that we just did it, okay, for her. She is a diver. Yeah, and then we're going to draw the free body diagram of this object, okay, when she is in the air. Now we're going to neglect the air resistance. Okay, air resistance is a huge thing. So every time we study in the book, we usually neglect the air resistance. When you study in the real world, you're going to put that thing back in. Okay, and this depends on the region. Right? Why do we neglect it? Because it's so complicated. It depends on the day, the time, the season. The air resistance, because air is a very fluid thing, because they change all the time. Because of the wind, the air, the pressure. So therefore, this thing value is always changing. Okay, then what you have to do is you're gonna draw. Okay, so this one is actually in your digital book. If you go there, you're gonna see the drawing, and you can be able to see. Let me go there and show it to you. So it is on this page, okay, 5.5-1, and what you have to do is to look, okay, into this, okay. So this is a page, okay. We just went through everything, after jumping, before she jumped, and here is the weight, the normal force, and the diver's force, the friction force, and the normal force. So your normal force and the weight, okay, they're not equal, because if they're equal, she won't go up and forward. Because the question already said the gear is accelerating up. Okay, so therefore your normal force got to be greater than the weight, otherwise she will still be on the board. And then of course you draw the free body diagram where we show the weight, okay, as soon as she is in the air. But then of course we neglect the air resistance. So you can see how the weight is going down because of the gravity, okay, is up there. So that's what I want to show you, where the interactive textbook page is. So you go to chapter 5, and I'll go to 5-1 problem, and you're going to see the same thing. Up in the air, there's only one. On the board, okay, she's got all of this. The friction happened because of two surfaces in contact. When she is in the air, there is no friction. Here's the author cut out the board here. All right, and then another one is your boy is running while flying a kite. And we gotta draw a free body diagram of the kite, and then diagram of the boy. So your kite is going to have weight. And then here is, of course, another force acting on it, so it will stay in the air. And then of course the draft is going to go that way, meaning like there's another force in the air that is pushing the kite to this way. So therefore your kite is going in that direction, where the guy here, which is the boy here, is pulling the kite. Okay, so his force is going this way, so therefore the kite, okay, because of this air in here, it will go to that direction. Okay, of course this is your tension because of this rope, all right, between this boy's hand, and then this kite is being connected with this rope, so therefore you also have a tension force. So you have a tension force exerted by the boy to the kite to the boy, two of them. Here in opposite direction, and then your lifting force by the air resistance, and then you also have the weight of the kite going downwards, weight of the boy going downwards, weight between the ground and the boy, there's a normal force, and then of course you have a friction force because of the contact between the boy and the ground. Okay, so this is the air is pushing in this direction. So now you have all of the forces in a free body diagram. Then we will get into Newton's second law. We're going to apply that. So we have many problems there. You will have to use, okay, kinetics, forces that cause the motion, kinematics, okay, all of the aspects of the motion, like your velocity, yeah, your location or position, velocity, and acceleration are kinematics. Only force is the kinetics. And we use both of them to solve the issue, yeah, which is in the problem. So we will solve the kinetic problem to find the acceleration, because kinetic is usually force, and force is again ma. And then we can use the kinetic force, kinematic problem to solve the velocity, displacement, time. Yeah. So kinematics, we usually solve the acceleration. Kinetics, we usually solve the force. Rectangular or coordinates, yeah, another one, because we always study x, y, z. In actual, we have another axis which is z, yeah, in 3D. In 2D, usually x and y, and of course we have different coordinate system, yeah. But I only gave you x and y for now, yeah. You also have nt and other stuff, but don't worry about that for now. Okay, so Newton's second law again, x and y direction, accelerations, they're very independent. Like in chapter 4 that we study the projectile, yeah, motion like this. And then of course we also study the motion that is going to go in one direction, and we use our sum of the x and y component of the axis. Yeah, this is x and then this is y. All the forces on the x-axis, sum of the forces in x-axis, sum of the forces in y-axis. Yeah, sum. Okay, then we go into problem 5.6-1. So we have a weightlifter, and she squats, yeah, motionless on a scale with a barbell, and here's your barbell held on her shoulders. This is a little one. Anyway, so first the weightlifter stands up, and then she lifts the barbell up and over her head, ultimately holding the barbell motionless. Yeah, because the weight is not that heavy here. So if the woman's weight is about, she has about 120 pounds, and your barbell is only 70 pounds, so she can definitely lift that up, yeah. And we are going to consider this situation here. So if the woman's weight is 120 pounds, the barbell is total 70 pounds. The first question is, what does the scale read when the weightlifter is initially squatting on the scale? Yeah. So let's say like we have to come up with the magnitude, yeah, and all you have to do is add this up, because your force, okay, is the summation of the forces, and we have force 1 and then we have force 2. The sum of the force is force 1 plus force 2. 120 plus 70 is going to give you 190 pounds of force. Then, and the next question is, what does the scale read when the weightlifter, after standing, she's going to stand, and then going to move the barbells up with an acceleration. Yeah, there's a force. Acceleration means she has a force, 9 feet per second square. So we start calculating it, your force ma, okay, and you are going to minus the weight, yes, because this again is the sum of the forces, yes, in that situation. So we have two forces. One is the force S, and the other one, this S is not friction, this S is a force, standing force, and then she has a weight, okay. So therefore we're gonna have a standing force is 70 pounds, because that's the barbell, all right. And then you will have to move this to the side, okay. So here is your mass, and then here is your acceleration. When you move this, okay, you are going to get 190 pounds, which is the total weight. Yeah, this guy is actually the total weight. Your mass, and then time 9, which is the acceleration, okay, of your barbells, and your barbells weight is 70, yeah, 70, and of course we divided with 32.2, yeah, and that is because of this feet per second, and this is a pound, yeah, so that's just conversion factors to equalize the equations unit, yeah. Now, because we have to produce our answer in pounds, so you will have to divide 70 with a 32.2, because we want to use a 9 feet per second square, okay, unit in addition to the pound here. So this is what you're seeing, the conversion, yeah. So I know that some of the students is going to ask, oh, why are we doing 32.2? Yes, because of the conversion factor, yeah. We will have to change the 70 into feet per second, yeah? And then of course, and then you're going to add it with 190, and when you calculate it, you get 210 pounds, all right, for this standing, yeah, force. So this 32.2 is actually, I would say, like feet, you know, because we have to cancel feet per second square, which is this guy right there, yeah. That's why we divided with that. So you will end up having pound at the end, yeah, because this 32.2 feet per second square, all right, is your acceleration, yeah. So why do you have to divide it? Is because we want to find, I think I should write this here for you, okay? That way you can see this, yeah, mass. It's just a conversion factor. And then minus, yeah, like this. Yeah, then this minus became plus because your W, okay, is minus on this side, yeah. So when you move to there, it becomes a plus right here, and we divide with 32.2 because one, yeah, acceleration due to gravity is 32.2 feet per square, because we use a feet per square for this unit, yeah, acceleration. So this is acceleration. Your mass is a weight equal to mass times acceleration due to gravity. So we use 32.2 to match the US customary system, yeah. Instead of 9.8 meter per second, we use meter per second square, we use the 32.2 meter per second square, which is this guy, yeah. And you will have to, of course, divide your weight with G to get M, yeah, because that is the M, by the way, yeah, that's not weight. You only have weight information here, yeah. So that's just a conversion factor. If I say that's a conversion factor, sometimes you don't get it. It's because this is mass, all right, and that is weight. You're given weight instead of the mass. Okay, so then the next one is the next question is what does the scale read when the weightlifter, this person, has the barbell up over her head? Now she's gonna lift it up, yeah, and we gotta come up with the weight. Doesn't matter she lift on shoulder or up above the head, your total weight is going to be this 2, yeah. Then we have another problem. So we have 6 figures, yeah, is right here, shown various, yeah, situation where a block is attached to a rope, yeah. So there's a block and it is attached to the rope like this, okay. And look at the rope, yeah, in a various situation here. So from highest to lowest, we have to rank it again. So the resulting tension. So again, tension can happen only if you have a connecting objects with a rope. Yeah, rope is a very important thing. So now that for the situation where the body, this rope can be any material, yeah, from metal to a regular, and then where the body has velocity, this velocity is constant. So we gotta note that for the situations here, the body has velocity, yeah, and with a constant, of course. And then we will have to rank it. So, yeah, so I'm gonna go over each one of them. So when you take a look at it, okay, we can see that we have a 6 situation, 1, 2, 3, 4, and then 5, 6. Yeah? So the first situation, you have a tension is 50 Newton is because of this guy shown here. Yeah, and of course this is a 20 Newton. All right, this is the weight of that block. Okay, and here is this rope. Yeah, therefore we have a tension, 50 Newton tension right here. So we know that that is a tension. Okay, there is no other force acting on it, so we can calculate that very easily. And then the next one, we're going to calculate tension, and here it is at an angle, and your angle is 30 degree, so therefore 50 minus 20 sine 30, and make sure that you do the same thing. Sine means that your resultant is right here, yeah, opposite side, not the adjacent. Adjacent means this side. So anyway, so we have a sine 30 Newton, and then if you calculate it, you will end up getting 40 Newton. This is less than that, yeah? So therefore, we're going to continue to calculate another tension. Your rope is here, the rope is right here. So the tension force is 20, the rope is right there, and you have another opposite, yeah, force right there. So we will have 70 minus 40 and 30. So now we have 50, 40, 20, and 30. The next one, rope is right there. You have a 2 tension here with 25 Newton on each, and one of them is moving with a velocity 4 meter per second. Yeah, so since they are balanced on each other, your tension force is only 25. Yeah, and here the same thing, and you have an F situation. Yeah, your F situation looks like this. Okay, and then I just want to show you where the rope is. All right, and then here is your 25, 25 going with the same velocity, but you can be able to see, right, 2 of them are right in there, which looks very much the same. Yeah, but when you look at it, you know that we have a 25 here and then 25 here. Yeah, and of course this is changing the weight into the mass, and then times of 4, okay, here, and you can be able to get, and that is 35 Newton. Yes, and here of course when you study this, okay, and I want to point out, like, you shouldn't have this in E. Okay, so that is a typo. I think I will just get rid of this. You don't have it. They are in equilibrium. Yeah, therefore we get the 25 Newton here, showing you your E is here. Yeah, because this is 25, and then your C is, I believe, 20. Yeah, we calculated it, and your F is 35 because of this velocity is there. Yeah, make sure that you get rid of this one. It's not, I think it's a typo. Of course, A is highest because we calculated 50, followed by B 40, followed by F 35, and then your D is 30. Okay, and then 25, and then the least is 20 for C. Yeah, so make sure that you calculate all of that. Alright, and then we're getting into a normal tangential coordinates. Of course, so this is just for you to just listen. Yeah, because we are getting into the anti-coordinate system. So let me check my curriculum. Oh yeah, sorry. You don't have to listen because we're not covering this anti-coordinate system. Yeah, in this. If you do see the question in your quiz, don't worry about it. Okay, I will definitely give you that point. So I don't think I put that in either. Yeah. All right. So I'm gonna go ahead and stop right here for you. Okay, for chapter 5.